Okay, let's do an application. I'm going to focus on two applications. And if I don't run out of time, I'll touch on a third one. But the two are going to be NMR spectroscopy and thermochemistry. They're about as different as you can imagine. NMR is used by all organic chemists. It is the standard. Thermochemistry is something you yawn about. Also extremely important. Okay, NMR, the first comment I'll make is that NMR is difficult. The experiment is easy. Getting the interpretation is difficult, and there are a huge number of errors in the experimental literature. People don't like to admit that, but especially in a place like natural products chemistry where you don't have the chemistry behind you, there are a lot of bad guesses. And it's hard. I have a great deal of respect for that. What is actually calculated are the chemical shifts. The chemical shift is essentially the magnetic field at the nucleus. It's a well-defined quantity that can be calculated. We could also calculate coupling constants. It turns out it's probably not worth it. It's better to get them empirically. They're rather ordinary, given that you have the geometry. Okay, if you look at an NMR spectrum directly off a density functional calculation, I'm just going to take a really simple molecule, nicotine. The structure is assigned correctly. It can't help but be. And the spectrum is assigned correctly. If you look at these, they're terrible. Experimental precision in the case of NMR is probably a few tenths, this is carbon, a few tenths of ppm. More important, the assignment errors where you really know you're right or wrong are a couple of ppm. You can clearly see that we're way outside that. They're no good. Now, there are people that continue to calculate NMR just directly from density functional or other theories, and they continue to publish it as trash. They're just no good. There's systematic errors in it. And you can deal with that if you standardize methods. And the method I've talked about, which is a density functional theory, we've actually done that, and we've parameterized corrections. There's nothing wrong with parameters, as long as they're carefully used. And we parameterize corrections such that we now can get carbon to about 1.7 ppm. That's getting close to being useful. We can get proton to about 0.15, and fluorine is much harder. Fluorine has tremendous variations with conformation. That's a much harder one to get right. Okay, if you now take a corrected scheme and you do the same thing, I just want to calibrate you. You'll now see they're really pretty good. Okay, so we now believe one has a scheme that works. Carbon 12 is that one. We now believe we have a scheme that works. What good is it? Well, let's ask what we can do. And one of the things that you can do that's easy is you can say, given that the structure is correct, is the assignment correct? And nicotine, it looked fine. The matches were perfect. Let me look at another really simple molecule. I'm grabbing these out of a single beautiful textbook about this, the NMR of natural products. This is chemazoline. The structure's right. The assignment is wrong. You can argue all you want, but it's wrong. There's a reversal. When you have RMS of 1.7, 3 times that is 98%. We're not that bad. So here's one task is given, I simply want to assign an NMR spectrum. I know the structure. That's really not the interesting task. Okay, let's get a little bit harder. NMR spectra can support or refute a structure. Here's a famous one. that is in the literature, in the textbook literature, and it's wrong. The molecule is luminol, and the structure that's drawn in about 90% of the places is that. If you look at the NMR here, let me use this as an excuse to bring it up in. Oh, actually, I started with that. Here's the NMR of luminol. I'm doing this on an iPad. Calculation isn't. And if you look at this carefully, you'll realize it's pretty bad. It's the number of lines. It's not that they're off by such and such. I've got 2 and 1. I've got 1 and 2. It's not a very good match. It's something like an error of 5 ppm. It's not a very good match. If you now go to look at, maybe it's not luminol, maybe it's a tautomer. And I'll get back to this one when I talk about thermochemistry. Here's another structure of luminol. It's the same molecule. I've simply flipped NH for I've done a tautomerization right here. And if you now look at its NMR spectrum, and I don't want to spend too much time going back and forth here. If you look at its NMR spectrum, it's now rather good. That's a line on top. These are both lines on top. That's a little bit off. It's now rather good. So one of the things you can do is to attempt to actually assign whether a structure is right or wrong. Let me do a one that caused a lot of stink in the literature. A little more complicated. It's a molecule called hexacyclinol. The original proposal was this. I won't go to the iPad here. The original proposal was this: a strange peroxide kind of structure. If you look at the NMR down here, it's pretty bad. Now, one of the things that theory can't do is say, well, what is the molecule? I don't know. But what I can do pretty definitively, if one gives me a structure and an experimental spectrum, I can tell you the chance of that spectrum being either completely reasonable or completely unreasonable. In this case, it's completely unreasonable. So this could have been discounted in about 20 minutes of computer time. It went on for a many-year literature fight. It's wrong. I don't know what the right structure is. Here is the current candidate of the right structure, and I can't pick on this as far as being bad. If you actually count batches of lines, they're fine. But again, this is to do this right, I have to decompose the spectrum and look more carefully, and I don't want to spend the time at this point. Okay. Another thing that theory can do is it can say, I've got 2 candidates. Now, this is a Japanese example, fairly recent. I've got 2 candidates. Which one is better? This is on the way to a natural product, or it is the natural product actually. And the paper actually had 4 candidates. I've just grabbed 2 of them. The correct one, which is this phenanthrene kind of molecule, and this one, which is an anthracene kind of molecule. If you want to try to decide, you simply look at the comparison. You'll see that this one is actually pretty good, and this one is terrible. There's a line out here which is completely on its lonesome here, whereas that is pretty good. I think the error here is something like 1.8 ppm. This one's something like 5. So here is an application where we can actually say something is reasonable or something is not reasonable. Okay. Let me turn to my second topic, thermochemistry. Thermochemistry is extraordinarily important in chemistry. one doesn't appreciate it, but if you want a reaction to go, it really has to be thermodynamically favorable or isn't going to go anywhere. So just the question of, is this reaction favorable, is it not favorable, that's important. It's also important to say what isomer, what structure, what tautomer is the one you're going to actually see. I know that chemists love to talk about kinetics, but there's an awful lot of chemistry that has nothing to do with kinetics. If I get to my last topic, I'll try to show you that. Experimental chemists, in particular synthetic chemists, don't do thermochemistry very much for a very simple reason. It's a destructive experiment. You've now spent 1 month making a compound, 100 milligrams, it's a lot, and you burn it. That's not appreciated. And so it's not an experiment that's done very often. It's done where you make huge amounts of compound. For example, the pharmaceutical industry does thermochemical measurements, but it's not commonly done. Now, in order to open up thermochemistry, I need to know something about structure. I actually need to know what the molecule looks like. And so I have to spend a little time on equilibrium structure. It turns out that that is one of the easiest things to calculate accurately. And in fact, if I look at the prime source of structural information experimentally in the literature, which is X-ray crystallography, theory is probably more accurate than that. X-ray crystallographic bond lengths, for example, differ by about 0.2 angstroms from experiment for small molecules. For big molecules, much, much larger. The theory is, in fact, able to go underneath those limits. And so structure is simple. I could give you tables and numbers. Let me just give you one photograph, or one shot. I should do this in Spartan. This is an area we've been working on, which is catalysis by lanthanides. And one of the things one did was to pull out every neodymium structure in the crystallographic literature. There are a couple of hundred. And actually just superimpose them with calculated structures. This is rather typical. That in fact it's really good. I mean, you're getting when you get far away, your little tiny angular things is causing distortions. But structure is something that actually is quite reliable. Now, so just do it visually. Now, when we have a structure of a molecule, we can now calculate its properties, and there is a difference now between what an experimentalist calls thermochemistry and what a theoretician calls that. An experimentalist does something which results in what he'll call a heat of formation. That is not a measured reaction. It's the measure of a hypothetical process where we relate a molecule to its standards. A theoretician will also relate to standards, but they'll be different standards. They'll be separated atomic ions and electrons. And so if you try to compare an energy, what you calculate from a theory, and a heat of formation, they look very different. If you erase the standards, if you cancel them, they're the same. Now let's ask what you can do with thermochemistry. If you knew something, I'll use this example. I apologize, these slides slipped off here. I'll use the luminol example, where I showed you that the NMR of luminol is wrong, and the NMR is this tautomer. The assumption was it's this tautomer. In fact, that tautomer is something like 10 kilojoules less stable than the tautomer that actually fit the NMR. This one, the third tautomer, is much worse. 10 kilojoules in a Boltzmann distribution is about 98%. And so what it's saying is if you actually had a distribution, if you actually had luminol, 98% of it is this. 2%, the one that people draw in the textbooks, is that. It also will help you find situations, if you have thermochemistry, it will help you find situations where you have tautomers or other kinds of isomers that are essentially identical. Now, here's my pyridone example. I use this for infrared. I said that when we looked at the infrared of 2-pyridone, it had an extra line. Well, the other tautomer is actually less stable, but it's essentially the same. So what this tells me is that a real sample will contain about equal amounts of both of those. And that's exactly what the experiment was telling us, that we had noticeable amounts of both of those. Just very qualitatively, to point to a real example, I mentioned before we were playing with neodymium systems, and the reason is a very practical one. These are catalysts in the production of synthetic rubber. And this is actually it's probably the most important use of lanthanides commercially. And the key thing with synthetic rubber is to get pure systems, either pure cis, which is actually the dominant important one, or pure trans. Mixtures tend to give synthetic properties that are not very good. So what can you learn from this? And I want to make 2 points about this. One is what you learn is qualitative. For example, what you're actually doing is you're exploring chemistry with computation. You're not looking so much at numbers, but you're looking for ideas. You're looking for what sticks out at you. And that's important because I think it's the same thing you do with experiment. Careful experiments are not only measurements. Careful experiments are also doing something and observing. In the case of the neodymium ones, I just give a simple example. I'm also deliberately putting fairly large molecules on here. I want you deliberately to see that you're not limited to tiny things. Here, the interesting thing was actually asking the question, is the reaction, the polymerization reaction, exothermic? Will it actually go as we've written it? Because if it won't go, if we're picking a catalytic system that it is not thermodynamic, since the molecule stays on the catalyst doesn't go away after one step, it stays there. Every step has to be thermodynamically, has to be exothermic. You can actually show that, and you can try to establish, well, which cases will be more favorable, which cases will be least favorable. This is what I mean by exploration.